Okay, everyone, we're revising section of forces, first of all about springs, and you can see from this diagram from an exam paper, we've got a picture of a spring before it's being compressed, and then during compression where we've got this weight here sitting on top of the spring. And we should appreciate that obviously the spring is being compressed or squashed, and that's due to the force which is pushing downwards from the load that's on top of the spring here. Okay, notice that when we draw these arrows, we can think of them as originating from a central point, which we'd refer to as the center of mass. Okay, what can we say about these forces? The weight from this object compressing the spring will be equal to the contact force, the normal force pushing back from the spring. Every action has an equal and opposite reaction. Going further with this then, from your equations, you should know that the force that's required to stretch or compress a spring, so they're both the same, is equal to the spring constant multiplied by the extension or the compression. So this could be the force that's stretching a spring, or it could be the force that's squashing a spring. Okay, the equation will be the same. You need to know this equation. If we think that the force is measured in newtons, like all forces, and the extension, the standard unit of extension, would be meters or centimeters or millimeters, let's say meters in this example, then K, the spring constant, will be measured in newtons per meter. How many newtons does it take for each meter of stretch or each meter of compression? So let's go back to these graphs here. 3 different springs. The graphs are saying how many newtons of force cause the spring to change in height. So if you need a lot of newtons per millimeter, then you would get less squash or less stretch of the spring for the same force. So this graph here is showing the spring which for the same amount of force gets changed in height, in other words squashed, the least. This one has the biggest spring constant. C is showing a spring that stretches more easily. C has the biggest amount of change in height for 8 newtons, and so this spring constant is less. You need less newtons per millimeter to make it stretch. Okay, let's apply what we've just used using another equation which is given to you. Elastic potential energy is half times the spring constant times the extension squared. You're given this equation. Let's go back here and look at the numbers. We've got 2 distances, and so from that I can work out the extension from 0.05 to 0.25 is 0.2 meters. I've taken one away from the other. The spring constant is 7 newtons per meter. I'm checking that I've got the same unit here, meters and meters, so that's okay. And I'm going to now calculate the energy by putting those numbers into my calculator. A half times 7 times 0.2 squared, don't forget that bit. Remember, you always need your calculator in your physics and chemistry and biology exams, and if we do all that, we'll get an answer of 0.14. I'm calculating energy. Any type of energy is going to be measured in joules. Okay, another calculation involving springs. When a force is applied to a spring, the spring extends by 0.12 meters. The spring has a spring constant of 25 newtons meter. Calculate, I need to do some maths, the force. So I need an equation that links force, extension, and the spring constant. We're going to use this one again. We're looking at our numbers. The spring constant is 25. The extension is 0.12. I'm checking that I've got the same unit of length here, so my units match. And then I simply need to do that on my calculator. 25 times 0.12 equals 3. The force applied to the spring is 3 newtons. Okay, next diagram is a glider, and you've got arrows for forces. It's very common to have to label these arrows or describe what the arrows are telling you, and we should be confident that this arrow, the vertical component of this force here, is the glider's weight. Better to say weight than gravity. Weight is the force that's caused by gravity acting on mass. A is the lift caused by the wings. Think about the size of these forces. If the weight and the lift are equal in size, the glider will stay at the same height. If the weight is bigger than lift, the glider will move downwards, and the lift is bigger than the weight, the glider will move upwards. We could add arrows to show that there's some sorts of forwards force and some sort of frictional or air resistance force. We could talk about a driving force. We could talk about air resistance or friction or drag. But we can pretty much sum up forces acting on objects with vertical components and horizontal components. Okay, make sure that you can explain how to do this experiment to investigate the effect of changing the force or the load on stretching a spring. We've got some apparatus here. You can see that the spring and the ruler are vertical, that the spring is lining up with point B here, and that point B represents 0 extension. When a force is applied, we'd be wanting to measure the extension of the spring. It was at B here, and the spring is now stretched, and the equivalent point, is at C here. So this would be the extension of the spring, and we could measure it and plot it on the graph over here. So by doing this and changing the force, so you would change this value, and that would be your independent variable, and you would measure the extension, and that would be your dependent variable. A control variable for this experiment would be to keep the same spring. So this is demonstrating Hooke's law. We're changing the force applied to a spring. We're measuring its effect on the extension of the spring, and we're controlling the type of spring that we're using. Here's the graph that's been plotted, and you can see that we've got a straight line, a linear relationship for most of the graph, which is what we would expect. Okay, in this part of the graph, we'd say that the force being applied to the spring is, we should say, directly proportional to the extension. However, you can see here that there's a problem, because directly proportional should mean that the spring goes through the origin of the graph, this line. The person making this measurement has made a mistake, and they've measured from the wrong point every time. So if your extension is out by 50 millimeters, effectively what's happened, they've measured the length of the spring plus the extension. So at load 0, the spring was 50 millimeters long, but this line should be here. So if this graph was correct, it would run exactly parallel to this line, but start in the origin, like this. And the curved part of the graph would remain parallel, like this. So although this graph is the correct shape, it's not in the right position. A mistake has been made. We could say there's been a zero error because they haven't measured from the right points, and that error applies to every single point on the graph. So we would need to take away 50 millimeters from every one of these results to make the graph be correct for this experiment. The straight line part of the graph is a direct proportionality, and we'd say once we get past this point here and the graph is no longer straight, we've reached the limit of proportionality, and this spring is no longer obeying the law which gives us the equation F equals KE. The K is no longer constant. Okay, let's go on and look at moments. So you need to recall that the moment of a force is the size of the force times the distance from the pivot. Forces are measured in newtons, distances are measured in meters, so the unit of a moment is a Newton meter. This example here is straightforward. Calculate the moment of the boy. It says anti-clockwise because if you imagine this individual's weight is the force which is acting down this way, it tells you that his weight is 400 newtons, and the perpendicular distance, the distance at right angles to the pivot, is 1.5 meters. So this boy's moment is 400 times 1.5, which is 600 Newton meters. Anti-clockwise, because if you imagine this person sitting on the seesaw, they're trying to make the seesaw turn in an anti-clockwise direction. In this figure 1, the seesaw would go downwards and hit the floor. In figure 2, the seesaw is balanced. You can see that there's somebody else on the end of the seesaw and they're sitting further away. Her weight is 300 newtons. The seesaw is balanced because the boy making an anti-clockwise moment, which we know is 600 Newton meters because we've just calculated it, his anti-clockwise moment is equal to the girl's moment caused by her weight, which is trying to make the seesaw move clockwise, and her moment is 300 times 2, which also equals 600 Newton meters. So an important rule: a seesaw or any levers will be balanced if the anti-clockwise moments are equal to the clockwise moments. Okay, the diagram's looking a bit more complicated now, but we're not being asked to do any maths here. The boy's mass is causing his weight to still act this way. The girl's mass is giving her weight, which is acting in this direction, and we know that the moment is these two numbers multiplied together and these two numbers multiplied together. So at the moment, if we imagine this divided into anti-clockwise and clockwise moments, on this side of the pivot where the boy is sitting, the anti-clockwise moments are 400 times 1.5, which equals 600. The girl's moment is 300 times 2, which also equals 600. But you've also now, because the pivot has been moved, you've got the mass or the weight of the plank being used as the seesaw times 0.25. So in this case, because there's the weight of the plank acting down this far from the pivot, there's going to be more clockwise moments than there are anti-clockwise moments, and the seesaw will move downwards this way. The side with the girl on will go down because the mass of the plank is acting through its centre of mass, causing a force, its weight, which is causing a clockwise turning effect. Let's apply what we know about turning forces to how stable or whether things will balance. You've got 3 model parrots here, and we can use this to apply the rule. The narrow rod, which is a pivot, and the line, the arrow, is showing the line of action of the weight of the parrot. This parrot will tipple over to the right because the weight is causing there to be a clockwise turning force. In Y, it will tipple anti-clockwise, whereas in Z, because this line of action of the parrot's weight is acting through the pivot, this parrot will balance. Okay, so that's an important rule about how things can balance or be stable. So if you take something like a cone with a nice wide base, its center of mass is low, its weight is acting down, and it's very difficult to tip the cone enough to make this line of force act outside the base. Things are stable if they have a wide base and a low center of mass, and will only fall over if the line of action of the object's weight acts outside the base, and that would cause a turning effect, a moment. Okay, so we're looking here at a combination of a spring, we've got a pivot in the center, we've got a balanced beam, and so we know that the turning effect caused by the elephant will be matched by the turning effect caused by the monkey over here. The moment of the elephant shape is its weight, 2 newtons, times the distance of the elephant from the pivot. We'd be tempted to write 15 here, but we mustn't do that because we need our distance to be in meters by dividing by 100. The elephant's turning force is 0.3 Newton meters. The question could go further and ask what the weight of the monkey is. What do we know? We know that the anti-clockwise moment is 0.3, and that has to be matched by the weight of the monkey multiplied by its distance from the pivot in meters. The monkey is going to weigh 0.3 divided by 0.2. The monkey's weight is 1.5 newtons. We can double check our answer here and say, would this balance? 2 times 15 makes 30, 1.5 times 20 makes 30, and so this toy, this balance beam with the animals on, will be balanced. The monkey is further away from the pivot than the elephant, so it should have a smaller weight, and it does. Our answer looks sensible. Higher tier people, you're going to get questions like this on your physics paper. We've got a diagram of a crane, we've got a pivot, we've got information about a load, and we've got 2 distances here and here. Okay, We don't know the value of this force. Calculate the moment caused by the load in the position shown in the diagram. So we know that the moment is the force or the load times the distance. We've got the correct units, 6,000 times 6.4. Get on your calculator. And that gives me a moment of 38,400 Newton meters. We're being asked in part B to calculate the pulling force that is needed in the steel cable to keep the jib horizontal. So if this is true, we know that the anti-clockwise moment and the clockwise moment caused by the forces either side of the pivot have to be the same. So we know that the size of the force, however big it is producing a moment of 38,400. Our mystery pulling force multiplied by 2.4 meters has to equal 38,400. So the force is going to be 38,400 divided by 2.4, which equals 16,000 newtons. This question has simplified the crane somewhat, because the jib, this part of the crane, would have its own mass here, and the mass of the jib would be causing another force down here. So in actual fact, this value would be smaller than the true value, because there's another turning force caused by the mass of the jib itself. Okay, that's the end of this week's video. If you've got questions, please talk to your science teacher. If you want to check out the moments and the springs section in Seneca, that will help you reinforce what we've been talking about.